Lab 5, Choose Your Own Adventure, I chose to track and model the motion of a falling slinky. The video of interest captures the movement of the free fall of a stretched out slinky. For my lab, I wanted to predict and analyze how the bottom of the slinky specifically would act as it fell to the ground. Intuition would tell you that the slinky would just fall to the ground as a whole, but I first modeled the experimental video and tracker to get an actual answer for how the bottom of the slinky fell. After gathering all the experimental data and observations, I used GlowScript to code a model experiment of how the slinky should act. Comparing the experimental graph and model data will reveal how exactly the slinky falls and how accurate the data and tracker was. For this lab, the most relevant physics concepts is without a doubt Newton's second law. According to this law, a change in momentum of an object indicates a net force acting on the object. In other words, an object at rest will remain at rest unless acted on by an unbalanced force. In the case of our falling slinky, two of the main forces acting on the slinky are gravity downwards and an upwards tension force. To code, I use the velocity update formula derived from Newton's second law, as well as the position update formula. To the right, you will see the video that I uploaded and analyzed in Tracker. I used the point mass function specifically on the bottom of the slinky to analyze the vertical position of the bottom of the slinky in the period that the slinky fell to the ground. Some initial conditions relevant for the code include a standard slinky mass of 0.25 kilograms and the initial position equal to approximately the origin. Another important point is that the slinky starts its fall from a position at rest, so its initial velocity equals 0. I divided the motion of the slinky up into two times, for the first one representing the top of the slinky falling while the bottom of the slinky remains at rest, which you can see in Tracker was the first 5.5 seconds. Then, from 5.5 seconds to 8.2 seconds, this represents the motion of the bottom of the slinky as it falls with the top. I used factors of these times to replicate the actual motion of the falling slinky, not the slow motion video, so the actual times are 1.2 seconds and 1.8 seconds respectively. Here is the data that I compiled into a graph from the tracker model of slinky motion. As you can see, the first half of the descent shows a non-moving bottom of the slinky, whereas after 1.2 seconds, the bottom of the slinky begins its descent as well. Next, I went on to model the motion of the slinky in a predicted model on GlowScript. To code the motion, I began with entering the initial conditions of the slinky, including the mass, velocity vector, and position vector. The standard acceleration due to gravity on Earth will be utilized in the force of gravity, which is 9.8. The j-hat vector represents the vertical direction of motion, and the drag constant I obtained was approximately 2.4, representing the air resistance as the bottom of the slinky falls. Next, I coded the first half of slinky motion. Here, the bottom of the slinky does not fall, so this indicates that the force of gravity is equal to the force of tension of the slinky, thus creating a cancellation of these forces in a motionless bottom of the slinky. This is reflected in my code as you can see it on the left. I then coded it in the relevant formula from Newton's second law that we discussed earlier in the video. Finally, I coded the second half of motion of the slinky. When the bottom of the slinky begins to fall, the tension force no longer exerts itself on the bottom of the slinky, and the forces working on the slinky are the downward force of gravity and the drag force of air resistance. This is coded on the left. Here is the model of motion in Tracker. As you can see, as the code runs, the first half of motion represents a motionless bottom of the slinky, while the second half represents the slinky's downfall. Here's the graph of that motion. After obtaining both sets of data, I graphed them on the same graph for comparison purposes. As you can see, the blue model of coded data is relatively accurate with a little room for error. This could be accounted for a number of reasons, including human error, wind, or a not so accurate drag force that I had to estimate for the code. To conclude, we can deduce that the slinky behaved in the way that it did solely because of the tension force acting on the slinky in the first half of motion. This tension force being equal to gravity creates an illusion of an object defying gravity in a way. However, we know that the physics of the slinky just indicates that the forces of gravity and tension force are canceling each other out, and without this net force acting on the bottom of the slinky, we know by Newton's second law that the bottom of the slinky won't move unless there was a net force acting on it. This net force doesn't come until the tension force goes away, and the forces acting on the bottom of the slinky are gravity and the drag force.